This is the first video on Chapter 24, Linear Transformations. And I'm going to do example 289. And we're defining a function t from R3 into R2 by t of x, y, z is 2x minus y and then 3y plus z. So the first component is 2 times the first component minus the second component in R3. And then for the second component in R2, we have 3 times the third component in R3. 3 times the second component in R3 plus the third component. And so we want to show that this is a linear transformation, so we want to show 2 things. Number 1, that t preserves vector addition, and number 2, t preserves scalar multiplication. So for the first part, we're going to suppose that we have 2 vectors in R3. So the first one is xyz, the second one is rst. Then we look at t of the sum of these 2 vectors. So we take the sum of the 2 vectors first, then we apply the linear transformation t, or the function that we're claiming is a linear transformation. So we add these 2 vectors. This is just vector addition. And then we apply the rule of t to this vector. So what do we have? We have 2 times the first component minus the second component, and then we have 3 times the second component plus the third component. Again, this is t right here applied to this vector. And we have this vector right here. To save some time and some board space, I skipped a step algebraically, but you can take this vector and you can write it as the sum of these 2 vectors. Then what do? We notice that this is just t of x, y, z, and the second vector is t of rst. And so t preserves vector addition. So if we add the 2 vectors first, then apply t, that is the same as if you apply t to each vector, then add these 2 together. Also, we'll take a vector in R3 and a scalar, and we want to show that t preserves scalar multiplication. So t of ax, what is ax? It's just ax1, ax2, ax3. And now we apply t to this. It's 2 times the first component minus the second, 3 times the second component plus the first. That is simply t applied to this vector, and it gives us this vector. Factor out the a, and now what do we have? T times the first component, 2 times the first component minus the second, 3 times the second component plus the third. That is t of x, y, z, or t of x. And so t preserves scalar multiplication, and so t is in fact a linear transformation. That's usually the last sentence in my proof, is to note that t is a linear transformation, but I was out of board space, so I stopped with that.